So the key idea of this paper is to propose a new method for 3D action recognition from 3D point clouds. And we do that using what we call T-patches, which are basically patches that evolve over time. Welcome to Talking Papers, the podcast where we talk about papers and let the papers do the talking. We host early career academics and PhD students to share their cutting-edge research in computer vision, machine learning, and everything in between. I'm your host, Itzik Ben-Shabat, a researcher by day and podcaster by night. Let's get started.
Hello, and welcome to Talking Papers, the podcast where we talk about papers and let the papers do the talking. Today, we will be talking about the paper 3DInAction, Understanding Human Actions in 3D Point Clouds. This paper was accepted as a highlight to CVPR 2024, and I am happy to host the first author of the paper, Itzik Ben-Shabat. Hello, and welcome to the podcast. Can you introduce yourself?
Yeah, hi. Thanks for having me. My name is Itzik Ben-Shabat, and when we worked on this paper, I was a research fellow at the Technion Israel Institute of Technology. I'm also the producer and host of the Talking Papers podcast, which is this podcast, and everyone is probably wondering what is going on. So I guess, can you introduce yourself?
Ha ha ha. That is a good point, Itzik. Our listeners are probably wondering what is going on. So I am an AI avatar generated by a company called Synthesia. My visual avatar is called Ronja, and my voice is called Alex Melodic. Obviously, I am not a real person, and all of my responses were written by Itzik as a fun exercise for the podcast. By the way, the episode is not sponsored or anything like that. Itzik was just looking for an excuse to try out this new and exciting technology. Let's continue with the episode. Who are the co-authors of this paper?
Okay, yeah. So the co-authors is a great team. One of them is a PhD student at the Technion, Oren Schrute. And the second co-author is my longtime mentor, my favorite person on earth, Professor Stephen Gould from the Australian National University.
What a great team. I know Steve. He is the best, isn't he? But I digress. So let's move on. In a TLDR format, can you tell me in 2 to 3 sentences, what is this paper about?
This paper, it takes on the task of action recognition from 3D point clouds. So you get a point cloud sequence, and what you want to do is basically say what action is happening in each frame in the sequence. And we do that using what we call T-patches, which are basically small patches of points, but they change over time, right? As time goes on, these they evolve, they move, they kind of change shape.
Interesting. Let's move on to the introduction section of the paper. What problem is the paper addressing?
Basically, the problem that this paper is addressing is the action recognition problem, right? This is very well known from the RGB world, where you get a video and you want to tell in each frame of the video what is going on, what is the action. Here, it's a little bit different because here we have point clouds. Now, usually point clouds are used in kind of, either autonomous vehicles kind of scenarios, or, we used to have the Kinect for gaming and for kind of indoor scene scanning. But whenever there's something that has to do with the action, there were like a lot of methods that either move on to skeleton analysis or they just process the RGB. And here, like, there's an opportunity to use point clouds instead, because, skeleton processing, you're basically depending on the quality of the pose estimator, right? If you got a good skeleton to begin with, then you probably get a good result. And these methods were great. But what happens when you don't have a great skeleton, when you don't predict the human pose properly? Or what if you don't even have a human? You want to judge the action of maybe a dog or some animal, right? So these won't work, or you need to specialize in those kind of things. Whereas here you kind of have the opportunity to use point clouds. And as for RGB, right, sometimes the RGB is either corrupt or you just want redundancy for, either safety or whatever reason, right? So this is like the motivation of doing these things directly from the point clouds. and I'm a point cloud person, right? I see point clouds everywhere, and I think they're a good solution to a lot of problems. So, I figured, why not?
But tell me, why is it an important problem?
Action recognition is an important problem to solve because, it can be used in many, many scenarios. I mentioned before autonomous driving, right? So this is a very safety critical application, right? That you want to have redundancy, you want to have several subsystems making a prediction and maybe kind of checking if they agree with each other. So this makes this method or problem set very, very important. Also in scenarios where, the data might be corrupt, the RGB data might be corrupt, maybe one of the sensors is damaged or is occluded or something like that. And that's where like the importance of doing the action recognition from the point clouds, that's where it really shines.
This is a very important problem. Can you share with me, what are the main challenges?
Well, there are a lot of challenges that you don't have in RGB, right? So first of all, point clouds are not structured, right? You don't have a grid, or you can set up a grid, but then it's like very memory intensive to get a good resolution. So the lack of structure is always a challenge. Also, when you scan something, you don't always have the same number of points between frames. So the number of points is basically non-constant, right? So in an image, you always know the number of pixels that you have, and you have a structure, so you can run convolutions, and you can do that with point clouds. An additional challenge that point clouds have, but in the temporal domain now, is that you don't know which point went where, right? In an image, you have the pixels, so a pixel is a pixel. Its location is constant, right? Sure, the scene moves, but the pixel is constant. But when you look at point clouds, right, you see a point in one frame, and then you see a point in the other frame. You don't know the correspondence. You don't know what moved where, right? Let's say you have a point on the shirt, then the person moved. Where is that point now, right? It's a completely different coordinate in space, which adds another level of challenge that we need to address here. And this makes it a really interesting research area to explore.
Okay, this sounds like a very interesting and challenging research area. What are the main contributions of this particular paper?
Right. So I guess you can say we have two main contributions of this paper. One is the T-patches, which is basically a novel representation for dynamically evolving local point cloud sets. And the second contribution is a hierarchical architecture that basically produces an informative spatio-temporal representation for sequences of point clouds. It basically takes the T-patches and inputs and gives out the action per frame.
I can't wait to dive in, but before we do, let's talk a little bit about related work. If you had to name one or two papers that were instrumental in writing this paper, which ones would they be?
Yeah, there's so many interesting related works here. If I have to name a few, I would say, well, first of all, PointNet and PointNet++, because these are kind of like, they started the whole, world of using neural networks and deep learning methods to process point clouds. This is like very seminal works. Definitely recommend the read. The PointNet paper is very easy to follow. And our method in many ways is very similar to PointNet++, which kind of like it's also similar to PointNet, but it kind of builds on top of it with this hierarchical structure, right? So just to like in very shortly, like basically what PointNet does, it takes the point cloud, it processes each point separately into like this high dimensional representation, then max pool to get a representation for a point cloud, right? So this is for a static point cloud, not dynamic one like we're using. And these methods work great. Like there are newer methods that are able to squeeze a little bit more out of data sets to get better accuracy for classification tasks. But I think they're a great start for anyone that doesn't know how to process point clouds. This is a great place to start. The other work that I also would send people to read is PSTNet, which are spatio-temporal convolutions for point clouds. It's from a group that had a lot of works in 3D action recognition using point clouds, and they basically had this nice way to learn a spatio-temporal representation So definitely go check that out as well.
These are very interesting papers, and we will make sure to put a link in the description below so everyone can check them out. Okay, now for the fun part, the approach. Tell us, what did you do and how did you do it?
Okay, yeah, let's talk about the approach. So I guess I would start by talking a little bit about T-patches, because I'm going to start to understand what we're doing. You're going to have to understand what T-patches are. Okay, so what is a patch, right? So a lot of methods that process static point clouds first extract patches, right? So you select a query point and you basically find either k nearest neighbors or some number of neighbors around the point, either like using a radius search or k nearest neighbors to get a patch, right? A patch is just a bunch of points that are close to each other. They might have other similarities like normal vectors, but let's for this case, let's just use the k nearest neighbor search, which is like the most basic one, and this is what we also used in our method, right? So this is a regular patch. So what is a T-patch? A T-patch basically, we actually give a general definition of what a T-patch is, right? That it actually tracks points over time using some unknown function, but actually modeling this function is very difficult. And we were able to show that you can actually use some very naive mapping function and still be able to learn very informative representations. And when I say naive mapping function, it's just k nearest neighbors, but just for the following frame, right? So let's say you have a point cloud from a single frame, you have a query point, you find its k nearest neighbors from that frame, and then you also find the k nearest neighbors of that point in the next frame, right? The only thing that you need to do now is set where is the query point in the next frame. So that's the closest point to the original query point. Now you have the patch and the query point in the next frame. You do it iteratively, right? So you do it for every 2 frames in the pipeline until you get kind of like a patch from start to finish, right? So the full T-patch is from frame 0 to the final frame. So this is one way of extracting the T-patches. Now, obviously, you can find better, more sophisticated mapping function than k nearest neighbors, but we showed that it's good enough to learn something very meaningful, and sometimes even a little better than if you have like the ground truth correspondences, which in most cases you don't have that, but in one of the data sets that we tried on, we had the ground truth correspondences, and it turns out that it's a little bit better to do the KNN search because it kind of adds a little bit of noise and serves as kind of an augmentation. But yeah, once we have those T-patches, then we can feed them into our hierarchical architecture. So the hierarchical architecture is basically structured by having several, we call it T-patch modules. Each module basically extract T-patches, feed those into a point net-like neural network, and gets, let's call it an embedding, right? It gets a vector, an embedding vector for each one of these T-patches, right? Then you feed those representation of each T-patch to the next module. And I should say that every module also subsamples the point cloud, right? So you don't need to compute all of the T-patches for all of the points in the point cloud. You can select a subset, and we select that subset using farthest point sampling, just to make it more tractable. And also there's a lot of overlap between the T-patches, so most of them would basically have they would be very similar anyway. So using farthest point sampling is beneficial in both of those regards. And then once you subsample and you get the T-patches and you get the representation from the network, you feed that to the next step of the hierarchy that again subsamples, computes higher dimensional representation, and so on, until at the end we basically pool over all T-patches, and now we have a representation, basically a vector for each frame of the input sequence. And now we can feed that into a classifier. In our case, it was a fully connected, several fully connected layers. and we output a prediction per frame. To train the network, we use the same losses of RGB-based approaches, which include frame prediction, cross-entropy loss, and a per-sequence prediction cross-entropy loss. And and then we train it on whatever data set that you need, and you can get a per-frame prediction for 3D point cloud sequences. It's that simple.
That is very clever and very non-trivial.
I actually should mention one thing, right? So the way we construct the T-patches, there is something that we call T-patch collapse, right? And what is T-patch collapse? T-patch collapse is a problem where two T-patches kind of converge into a single patch at some frame, right? So they start off different, but then things move around. And then because we're using k-nearest neighbors, then they may end up being in the same patch, right? And what it does is basically kind of downsamples the data over time. And we wanted to avoid that. Now, to avoid that, we basically proposed this, what we call the bidirectional T-patches, which are essentially the same as the original T-patches, but we run it once from start to finish and the other time from the end to the start, right? So basically those patches that collapsed over time, now you have them when you look at the other side. This usually happens, or it becomes an issue when you have either a very fast motion or a low frame rate, and I think this is like a solution, but I think there's a lot of opportunity there to kind of improve on our method, to find something better or smarter using tracking or something like that to avoid this kind of collapse problem. But even with this problem and the bidirectional solution, we managed to get pretty decent results.
Super interesting. Let's move on to the results and experiments part of the paper. What experiments did you do and how did you perform?
We experimented on several data sets. The first one, which we used a lot for, the ablation study and all of kind of the first line of benchmarking, was the DFAUST data set. The reason we chose it is because it's a scan data set, but it has a lot of similarities to kind of synthetic data. You have the point level correspondences. It's very clean. It's very dense. There isn't a lot of noise. So you can really kind of have a grasp on like what is going on, right? How are the different methods are performing. Obviously we got state of the art result, but that's not the issue here. We did, so when we, and I should say, like, basically what we report is top 1 and top 3 accuracy, and mean average precision, right? And we showed that actually, like, one of the interesting finds here was that if you just process each frame separately, right? Use like PointNet or PointNet++ or 3D MFVNet or these kind of methods that work separately, you get something pretty decent on this dataset, right? You get like 50, 60% accuracy. Not great, not the worst, right? Better than random, obviously. But even if you add just a small temporal smoothing kind of prior, so just take all of the vectors that you get from your standard PointNet and just kind of average or just run a small convolutional kernel over the temporal domain, you already get quite a nice boost to around, 60 something or 70% accuracy, right? Which is nice. But we showed that actually our representation with all of the T-patches and the hierarchical structure manages to give a very significant boost over the rest, getting to almost 90% accuracy on DFAUST, which is pretty good because DFAUST, it's very kind of, so it's a data set of people performing different actions. So jumping jacks and raising the knee and moving the hips. And the first and last few frames of every sequence, they almost look the same. The person starts with this kind of neutral pose and either gets back to it, at the end, or kind of rests, or kind of, there's like a very small transition in the beginning at the end. So getting around 90% is pretty nice. The second data set that we worked on is actually one of my old data sets. It's called IKEA ASM. IKEA ASM is a very challenging data set. It's a data set of people assembling furniture, IKEA furniture, like the name suggests. And it's basically captured using a Kinect sensor that's positioned statically and takes the sequence of the scene. The reason it's very challenging is because when people assemble furniture, they tend to have like these very complicated poses and like gestures and movement, and things occlude each other. So you have a lot of distractors in these data sets. So this is a very challenging one. And we managed to get decent performances here, right? Like, it's not great. Like, it's around 50 something %, which outperforms all of the other baselines we tried. But I think this result kind of highlights that there is a lot of work to be done here, a lot of opportunities, I would say, because this data is very challenging, right? In our case, the main challenge is the motion that people are moving. Some actions are very fast and some are very slow. So if somebody's reaching to pick up a part of assembly, he would do it kind of quickly. But then as they rotate or like align the part to the rest of the assembly, that might be slower because they need to kind of focus and concentrate. So these differences in pace, they're very important and may affect the results.
This is very interesting. Please continue.
There are two additional data sets that we tried it on. So one of them was the MSR Action 3D data. The results on this data set are comparable to other methods. I guess it's mostly because of the size. It's not that big compared to IKEA ASM, which is much bigger. We also tried on another data set, the NTU 60 data set. This one is much, much bigger. And we showed that we were able to get good performance even with using just a subset of the data. But if you use all of the data, we are comparable to existing methods that use transformers. I think the size of this data set is massive, and it's very useful for a lot of methods. But for us, I guess the takeaway is that we were able to extract those features or those meaningful features, even when you use just a small subset of the data, right? It doesn't have to be huge. And a lot of time, this is a problem, right? So capturing these data sets is very challenging, very time consuming. I know because I collected 2 of those in the past. So it's actually nice to have a method that can work with just a subset of the data, and still give decent performance.
In which cases does the method fail?
So yeah, the method. Obviously, like any method, you have fail cases, right? So as I said before, I think the main kind of limitation or problem with the approach is currently. Right, it's obviously solvable in the general case that we proposed, but in this particular case, where you use the KNN, then basically the construction of the T patches is limited with respect to the frame rate and motion speed. Right, so you can lose T patches, or they won't track over time well if things are moving fast and the frame rate is low. So we had some fail cases, particularly in the IKEA ASM data set, where the motion was very fast. So it didn't work as well because the T patches just went around. They didn't really follow what they were supposed to. Obviously, we see solutions, right? Like you can basically model the function, the mapping function between frames in a different way, and that may help. But we left that for future work. So these cases where the motion is very fast is our main fail case that I think provides opportunity for others to continue our work.
Any unexpected or particularly interesting findings?
Yeah, interesting finds. Wow. Yeah. So we had something like really nice. So we did a GradCam visualization. So GradCam basically kind of visualizes the gradient magnitude on each of the points. And what was really interesting was we ran that on the DFAUST dataset. And what was really interesting was that we saw that it focuses on things that humans would focus, right? So if you look at the jumping jack action, right, it would focus on the legs and a little bit on the hands. And if you look at like the hips motion, it would focus on the pelvis area. It was really interesting to see that it actually kind of highlights those regions as really important for that action recognition. Yeah.
Let's move on to the conclusions and future work section. How do you see the impact of the paper going forward?
Yeah, conclusions, future work. So, well, I think this is kind of a growing area of research. There aren't that many works there. It's not that crowded. I think that this work could open a lot of research, like I mentioned before. So what is the best way to construct these T-patches that we propose? How can we model mapping functions? Maybe even can we learn a good mapping function between frames? I think these are all interesting questions. And I think that if we answer those, we contribute to action recognition, but maybe also other questions that deal with dynamic point clouds. And yeah, I hope the community adopts this research direction and continues our work further. Yeah.
And now for your favorite part of the podcast, what did reviewer 2 say? Please share some insightful comments that the reviewers had.
Yeah, so we had a great batch of reviewers, and they had very interesting comments. So one of them was actually about why didn't we use transformer architecture, and it was actually interesting. We tried using a transformer architecture on the DFAUST dataset, and we saw that it was actually underperforming compared to our hierarchical architecture. So that was actually surprising, and one of the reviewers requested it, and we added it to the paper. I think this is mainly because transformers, they benefit from a lot of data, and in these cases, we just in most of the data sets we don't have a lot. Maybe in the NTU data set, if we tried, then maybe that would have worked. But this is massive amounts of time for training. I haven't mentioned this, but it takes a long time to train. Mainly because of the T-patch construction. After you have the T-patches, then it's pretty fast. So KNN so we use something very fast, but still it could be faster to get that running. Another comment that the reviewers had was how to kind of like look at effects of what happens with the occlusions, which we added to the paper. So we occluded a part of the data set, and we added an experiment. Not a part of the data set, a part of like all of the frame, but a specific region, and all these kind of occlusions effect that you do get in real life. And I think in IKEA ASM you have that naturally, but it was nice to have like a controlled experiment where we could see those effects. They were also really interested about the bidirectional T-patch, which it doesn't always help. So it helps a lot when there is the collapse problem. But if there isn't the collapse problem, it's pretty much the same, but maybe sometimes a little bit worse than the original approach of just one directional patches. Overall, it was a very positive feedback. We added those experiments, some more visualizations, and the paper ended up getting accepted. So yeah, it was a really good batch of reviews.
Before we finish, if you had one advice or tip to give a young researcher, what would it be?
Yeah, it's going to sound so, fairy tale, but I think the best tip that I can give young researchers is follow your passion. Find a problem that you find interesting, right? This is your PhD. This is your research. You need to be passionate about your research. And if you are, then all of the other problems you'll find a way through, right? When you're passionate about something and you want to do it, you just push through the challenges. So just find that, right? And also like find your why. Try to find why are you doing those things? And if you find that why, it will help you get over a lot of challenges, because, as researchers, nothing works at the first try, right? There's a lot of hurdles to get over, some of them technical, some of them more principled, and a PhD can be really difficult. So find your why, find your passion, and go with it, right?
We should also mention that this project has received funding from the European Union's Horizon 2020 Research and Innovation Program under the Marie Sklodowska-Curie Grant Agreement. Okay, this is an excellent time to wrap up. Itzik, thank you very much for being a guest on the podcast, and until next time, let your papers do the talking.
Yeah, thanks for having me, and thank you. Thank you for listening. That's it for this episode of Talking Papers. Please subscribe to the podcast feed on your favorite podcast app. All links are available in this episode description and on the Talking Papers website. If you would like to be a guest on the podcast, sponsor it, or just share your thoughts with us, feel free to email talking.papers.podcast@gmail.com. Be sure to tune in every week for the latest episodes. And until then, let your papers do the talking.